Thank you, everybody. On the 24th of August, at about 1 in the afternoon, my mother desired him to observe a cloud which appeared of a very unusual size and shape. A cloud from which mountain was uncertain at this distance was ascending, the appearance of which I cannot give you a more exact description of that by likening it to that of a pine tree, for it shot up to a great height in the form of a very tall trunk, which spread itself out at the top into a sort of branches, the force of which decreased as it advanced upwards, or the cloud itself being pressed back again by its own weight, expanded in the manner I have mentioned. It appeared sometimes bright and sometimes dark and spotted, according as it was either more or less impregnated with earth and cinders. The cinders, which grew thicker and hotter the nearer he approached, fell into the ships. Together with pumice stones and black pieces of burning rock, they were in danger too, not only of being aground by the sudden retreat of the sea, but also from the vast fragments which rolled down from the mountain and obstructed all but the shore. The fresco you see behind you is one that was made in the 1800s, but the words themselves come unsurprisingly from the event itself of 79 AD, the destructions of the towns of Pompeii and Herculaneum, and the eruption of Mount Vesuvius. So the story that we kind of have shown you just there were letters written by Pliny the Younger and his mother. So this is a painting showing them, the painting done again in the 1700s, but basically recounting what happened during the 79 AD eruption of Vesuvius. But why am I showing you a piece of artwork and also some letters? This is a data science conference. Well, for me, and for many volcanologists, this represents the very first data point in modern day or historical volcanology. It's an observation, it's words, it's emotion, but at the same time, it is data. And so for us, this actually founds many, many principles that we know today in volcanology. We know so much about the eruption of Mount Vesuvius in 79 AD purely because of these observations from Pliny himself. In fact, the eruption style that we now coin to a volcanic eruption with a large eruption column above it is called Plinian. That is where that term comes from. A Plinian eruption was named after the accounts of Pliny the Younger, as he was basically accounting what happened to his uncle, Pliny the Elder, who died during the eruption. But this is the volcano as we know it today on a much less hazy day than what we have it. But from looking before, it looks like the clouds are clearing a little bit and we can see a little bit more of Vesuvius today. But this is not just a historical volcano. It is very much a modern day volcano as well, and in some accounts considered one of the most deadly volcanoes in the world. That is not to put the fear into you for those of you who have plans to go to Pompeii or Herculaneum maybe tomorrow or over the weekend. But primarily it's called one of the deadliest volcanoes on the world on account that it's surrounded by a few million people by the metropolitan area of Naples. But a lot of people think that Vesuvius last erupted in 79 AD and that was it. Well, actually, there have been over 30 eruptions in that intermediate time. The most recent of them, just in 1944, during the Second World War, and you can see these fantastic photos of planes, and there's also some blimps in the sky during this eruption. A bit prior to that, in 1906, an eruption of Vesuvius actually resulted in a cancellation of an Olympic Games that were meant to be held in Rome in 1908. But the Italian government had to divert so many resources and funding to the city of Naples from some of the destruction that Italy could no longer host the Olympic Games, and instead they were hosted in London in 1908. So I'm not here to talk to you all about Vesuvius today, that's not the point. But this is to give you an idea that not only is this a historical volcano, but it is also a modern day volcano. So as my introduction before, my name's Sam Mitchell. I'm a volcanologist, science communicator, marine scientist. But the reason I'm standing in front of you here today is I want to convince you that geoscience is the most important science of all, and that our data is the most important data that you should all be analyzing. So no, but hopefully it's a chance to for you to dive into a different topic that you don't always do. We're going to do a deep dive into the kinds of data that we collect in geoscience, but more specifically in the realm of geohazard, and we'll break down what that term exactly is in a second. So we're going to look at the kind of data sets we collect, what the future of them is, what challenges we face, and why I'm going to put it all on you to tell me what functions in JMP can solve my problems and everybody else's problems in this field. So let's get started. What actually is a geohazard? Essentially, the hazard is the physical phenomena, the movement of mass or energy from one place to another. It is a physical process. It is not the same as risk, and you might know this from your own fields. But hazard and risk in the geoscience world, two very, very different things. The hazard being the physical phenomena, and the risk being a probability of some kind of impact, either to a community or some form of environment. Hazards themselves cannot be directly prevented or stopped in most cases, particularly when it comes to earthquakes, tsunamis, volcanic eruptions. Other more climatic kind of hazards can potentially be mitigated in some way. So even though we can't prevent the hazard, we can potentially decrease the impact of the risk itself. Generally, geohazards are divided into two categories, tectonic and meteorological. We're going to focus today mostly on the tectonic side of things, so this is our volcanoes, earthquakes, tsunamis, but I'll focus most of my time on volcanic eruptions, as that is what we have in the background of our conference over the last couple of days. And I will say I have to thank everybody in this audience, whether I've interacted with you or not, because I think I've learned more in preparation for this conference in the past 48 hours than I have in the months that I knew I was coming here, because I have learned so much just from observing and watching and listening to all of the talks, the lab experiences, the plenaries as well. And it makes me realize that everybody in this room, whether you're from biology, engineering, manufacturing, chemistry, pharmaceuticals, everybody's just kind of really excited about data and how we analyze that data. So hopefully I can get you excited about this data as well. So the kind of key points we'll go through today: how has the world of geohazard data actually evolved from that very first observation from Pliny the Younger and his letters? Where are we now today? What type of data sets are we actually dealing with, and the variety? The individual data sets may not be complex on their own, but when you bring them all together to try and use them for monitoring, they can be very, very complicated. What are some of the limitations in our data analysis, whether that's physical, digital, does it come down to personnel, skills, capability, or the fact that we don't know JMP exists until you come to a conference like this? And I realized that I could have done 9 months of my PhD in about a week. So yeah, hindsight is a wonderful thing at times. This is kind of one of the final lines we'll come to, which is what we really want and the main aim. In geohazard, we want continuous analysis of real-time, autonomously collected, multivariable 4D data that's available for integrated pattern recognition, forecasting, and mitigation. A small goal, right? So that's kind of where we would like to get to eventually in the future. But at the very end, we're going to come back to the original thing we talked about, these observational data points, and is our understanding limited to only the physical data that we collect from scientific instruments? So let's jump into the world of volcanoes. So there's a couple of very simple kind of lines on this graph, but we'll go through them. So we're looking at the number of volcanoes that have been identified from 1400s relatively up to the present day. These are the number of volcanoes active per year. Now, if you were to show this to anyone, you go, well, that's a problem. The number of volcanoes are exponentially increasing as we are. But there's another very key line on that, and that is global population. Global population is trending with volcanic activity. Correlation does not equal causation, of course. But the reason this is because we are identifying more, because there are more people in the world. We are in more places in the world. We have more scientific instruments on the ground. We are detecting them more. We have things in the sky now to help us in that effort as well. So it's not surprising that we've seen this boom in the number of volcanoes that are erupting per year purely because we are doing more and we are learning more about them. You'll see a bit of a plateau there, though, around the 1900s, just in the top right there, kind of the zigzag line with the red average line running through it. The number of volcanoes that we were aware were active per year kind of stagnated around 60 per year during the 1980s, 1990s. It's no surprise there was a bit of a boom after the Second World War in the 50s and the 60s. But there was this stagnation in the 80s and 90s, and then it jumped up again around the year 2000. And this data doesn't quite go to modern day, but again, it's now stagnating a bit. But I'll explain what that jump is in just a second. But let's break that data down a little bit more. We know about more eruptions now, but actually we're better at identifying the smaller eruptions, because the bigger eruptions are normally somewhere locked in a historical archive or some kind of narrative, as we saw from Pliny's letters from 79 AD. So the biggest eruptions are actually very stable through time. If you look at that line on the bottom, that is the number of eruptions over a given size. And this size is around 1/10 of a cubic kilometer. So I'll tell you that is a lot. The 79 AD eruption of Vesuvius was about 10 times more than that. But these are still very big eruptions. And so that stayed relatively consistent of around 1 or 2 per year for the last couple of 100 years. So that's kind of our verification that actually the number of volcanic eruptions is not increasing because the biggest ones are keeping along that line. It's not just in volcanics that we see the same trend. We also see it in earthquake and natural disaster data. So this is a similar kind of trend. As global population increases, as we put more instruments on the ground, we are detecting more earthquakes, and we're also detecting more natural disasters because there are more people in more places around the world. Now again, that seems to stagnate from around 2000 onwards and level out, and that's because we're also now better at preventing a natural disaster. We're better at preventing disasters by evacuations, by better building codes, by evacuations, by increased resources, better healthcare after the events of natural disasters, the reduce of famine. So we're starting to level off the number of natural disaster events per year as well. This is also reflected in tsunami data. This graph's a little bit more convoluted, binned by numbers of tsunamis recorded over a period of time, essentially the number of tsunami events per 100 years in each of those gray boxes. But again, we can see this increase in the number of events recorded, tracking with that black line of global population, and that is also set to increase. Tsunamis are an interesting one because even more so than eruptions and earthquakes, tsunamis are incredibly well embedded in historical data and observations as well. We know a lot about tsunamis because of what people wrote in history, whether it was more of a romantically written piece of the sea rising and swallowing the village. It is still a historical observation and a data point for our graphs. So we should not underestimate the power of those historically written records. And if we were to put all natural disasters into one single graph, we see that same trend again, kind of an exponential increase through the 1900s, and then it's starting to level off and even decreasing into the 2000s as we're better at preventing natural hazards on a whole. So what are the different factors that actually impact the kind of data that we're collecting in terms of geohazards? We've explained what the geohazards are, how many are happening per year, but there's lots of factors that come into what data we actually collect. The first of all being the actual collection itself, the number of different data sets, the variety of different instruments that we need to collect that data. You'll see it particularly with volcanoes in the moment. The number of data sets that we can collect from volcanoes is incredible. Tsunamis and earthquakes are a little more limited, but volcanoes produce a lot that we can measure. The capacity to be able to collect that data. How many people? Do we have the skills? Do you have the training? Do you have the infrastructure, whether that's a physical building or the digital archive data storage space? Do you have the finances and the resources and the backing of the government or funders to be able to collect that data? The choice. We might not always want to collect all of the data we would like. We have to limit and we have to prioritize. So what data do we choose? Are we trying to prevent a particular impact or prevent a particular risk and decrease that probability? Or are we just interested in getting the most data possible. So we're always having to consider these 3 big C's when we're thinking about geohazard data. And pretty much all of those come down to primary controls of finance and the people involved and where it's coming from the top. Most geohazards are run through, geohazard observations and data are run through observatories. So this might be a geophysical institute, a volcano observatory. For example, here in Italy, we have INGV, which is the National Institute of Geophysics and Volcanology for Italy. And so they are in control of all the data collection, but they are also reliant on their funding coming from the government. So there's geopolitics involved, international collaboration, relation, also public trust. The more the public trust these kinds of agencies and observatories, potentially the better educated your population is, and the more your government and funders may want to invest in that kind of equipment. But I said before there was one major shift at the very end of the 20th century. We hit 2000 and something big changed, which meant we were basically identifying more and more volcanic eruptions. And that was satellite data, remote sensing. This completely changed the game of how we monitor and observe volcanoes around our planet, because it gave us an ability to basically monitor everywhere around the world with some varying degree of a spatial resolution and also a temporal resolution. So we could now identify eruptions around the world in places that were very remote or inaccessible before. So remote sensing has completely changed the game over the past 20 years, and now we pretty much can say, without a doubt, we know how many volcanoes are erupting around the world at a given point in time. In fact, our remote sensing has gotten so good that we have better maps of the moon and Mars than we have of our own seafloor. We have Mars mapped down to 5-meter resolution per pixel of the whole planet. The moon, we have areas of the moon mapped to a meter resolution. That's the size of this table next to me in terms of a pixel on the moon's surface. We know more about those planetary bodies than we do of our own seafloor because the ocean's kind of in the way when it comes to satellite data. Even having said that, we're making massive advances in the data sets of collecting seafloor data as well. So we're mapping the seafloor at a greater rate than we have ever done before. At the moment, we've mapped about 27% of our global seafloor. But for you as the data scientist in the room, I just want you to imagine how much data is physically contained within those 2 plots you see up there for the seafloor of resolutions of maybe 10, 20 meters and of the whole surface of Mars down to 5 meters. It's a lot of data. But for volcanic eruptions, we're now in this kind of time where we're starting to compile everything we know. And there's one program that's doing this incredibly well, and it's the Smithsonian's Global Volcanism Program. And it is their job to compile all of the data from these volcano observatories around the world. So they can put out bulletins every week or every month telling us how many volcanoes are erupting around the world at a given point in time. So let's have a look at some of those basic stats. There are over 1,300 active volcanoes around the world that have erupted within the last 12,000 years, with around 10,000 confirmed eruptions. That is a lot. Now, when we say geologically active, we usually mean within the past 12,000 years or so. Our most recent period of geologic time, the Holocene. So my active is not the same as your active, like I say, if you're going to Pompeii tomorrow or some other day. But the reality is about 32 volcanoes are erupting around the world on any given day. The reason why you don't hear about this is because most of them are in those remote locations that satellites are helping us to pick up. They're in the eastern peninsula of Russia in Kamchatka. They're in the Aleutian Islands of Alaska, in the middle of the Pacific Ocean, down in Antarctica. And they're not making the news because they're not causing impacts. They're not posing risk. So there are many more volcanoes erupting around the world than you might consider. And in a given year, maybe up to 90 or 100 volcanoes will erupt. And then the key points on there are these 10 volcanoes with over 1 million people within 5 kilometers. And it's no surprise that Vesuvius on our doorstep is one of those. If you're interested about this, you can just look up the Global Volcanism Program or follow that QR code, but it can basically give you information about any volcano or eruption you are curious about. So if you're traveling, check out this website and you will be able to actually find out the facts you want to know about that volcano direct from the volcano observatories. Also, if you want to check if it's maybe going to erupt whilst you're on vacation. But here's just an example. That QR code is there again, so you can do a breakdown and you can have a look at what volcanoes were erupting within this year. So this is an amazing data set. It's compiled all those volcanoes, all of those eruptions into one place, and it has information about how long the eruption was, how big the eruption was, the type of magma that was involved, the chemistry as well. It's an incredible source. And so for me, what did I do? Well, I was a new JMP user. So I decided to basically take that entire data set, put it into JMP, and see what I could do with it. And immediately I was able to, pull up incredible distributions of lots of different data. Just as an example here, I wanted to look at the biggest eruptions in our record. So this is using one of the indexes. I've highlighted basically the biggest eruptions around the world. And you could see then that I would be able to use that to look at different parameters, how big the eruption was, how long it lasted, what year, what volcano, and the types of eruptions. I could then also look at it, of course, using more multivariable scatter plot analysis. It's very chaotic. There are no filters on this whatsoever. This is the raw database just thrown into a scatter plot matrix. But it just goes to show how very quickly we can use that incredible data compilation to start learning about stuff. Again, we'd need to filter this down, but I could do principal component analysis to look at how different volcanoes might be related to each other based on size, chemistry, different eruptions from the same volcano, what are the relationships there as well. And there's a whole host of other things I could do. Of course, this is spatial data, so I can plot this on a map as well, and I can look at variations in what volcanoes are erupting in certain places around the world. And I don't even need to put a map underneath there for you to see the coast of the Americas over there on the left. So it just goes to show there is really an incredible amount that I could do even just with that one database that is publicly available just at the download and dragging it straight over into JMP. Now, a volcanic eruption, it's fine to compile all the world's volcanic data, but every single eruption also has its own data set. Every single eruption comes with a huge data set within it as well. So I'm going to take you through my recipe for an ideal volcanic eruption. No volcanic eruption is ideal. But if the volcano is going to erupt, there is an ideal way which it would erupt for us and let us know it's going to erupt. So the first thing that's going to happen is a swarm of small earthquakes deep down, maybe weeks in advance of an eruption. Lots of small, hundreds and thousands of small earthquakes that are tracking volcanic magma moving through the crust. Maybe those earthquakes start to become shallower in those leading weeks, coming closer towards the surface. Maybe the ground is then starting to inflate and we're able to detect that inflation because you're moving magma and material into the ground, and GPS stations are able to detect those small changes. And you might be able to make evacuations from a certain area where the ground is inflating. Possibly there's a small plume of steam or vapor or volcanic gas coming out of the summit of the volcano, but it's not fully erupting at this point. Maybe there's changes in thermal signatures at the summit that we can pick up with infrared cameras. And now the earthquakes are becoming very, very shallow. They're getting very close to the surface. We're maybe hours away, and we can get any final people that we need to out of there and start putting in, full exclusion zones around the volcano. The eruption begins with expected styles, and the evacuations have taken place, and we have been able to prevent those high-level impacts and cause lots of mitigation of risk. That's the ideal scenario. But there are also lots of other signals that volcanoes can give us to tell us they may be about to erupt. So we talked about earthquake swarms, we talked a little bit about inflation, and they also deflate as well. Imagine a volcano breathing. Essentially, they do breathe. They're full of gas and fluid, so they go through these cycles of inflating and deflating. We can measure the volcanic gases that are coming out of the summit, what the chemistry of those gases are, but also the changes, the ratios of different gases to another can tell us how magma is moving. Groundwater. If there's groundwater around an area, we can look for changes in chemistry, changes in temperature in local aquifers and rivers. Changes at the summit, visual and thermal imaging. Is there something coming out of the volcano? Something might be happening if you see it coming out of the volcano, it's no surprise. Thermal imaging can be incredibly useful as well. And then long-term changes by satellites, doing passovers maybe once a week and looking at the change from one week to the next. So those two pictures you see up there from a report from the USGS, it gives an example of all the different types of hazards and then all of the different ways that we monitor those hazards. So you can see it's cameras, satellites, tilt meters, GPS stations, seismometers, ground surveying, physical observations, even down to webcams. But all of these kind of tie into, again, what I talked about before, the coverage, the cost of the instruments, how do you maintain them? Can you automate those instruments and that data collection? Is there an imbalance in where those instruments are placed? Do you have more at one volcano versus the one next door? Do you have the infrastructure to do repairs or to even collect the data and then to analyze that data as well? So we're going to give an example now of what's been happening over at Kilauea volcano on the island of Hawaii. So for the past year, just over a year now, Kilauea's volcano has been producing an incredible display of lava fountains, sending material over 1,000 feet into the sky and then falling back down, forming lava flows. There have been over 43 episodes as of a couple of days ago. This infographic was from the 1-year anniversary just back in December, so 38 episodes by this point. And this gives you an idea of just how incredible those lava fountains have been. Every single lava fountain episode has its own series of data, and we'll go through what those are in a second. But the Hawaii Volcano Observatory has also been monitoring this volcano for the entire time. So between each of these individual episodes, they are continuously collecting data as well. So now, as we go on to the next slide, I want you as data scientists, statisticians, to just think about the variety of the different data sets, what the data sets actually are. Are they an imagery data set? Are they a point vector data set? Think about what the data actually is and what the variety is. So this is all of the data being collected continuously over 2025 and still today. And I'm going to apologize for the size of that text, but I need it because I need to be able to fit all of these things in. So this is going to be quite a lot, and we're going to get through this as quickly as possible. We have GPS data from our tilt meter stations. That is an XYZ time series data set of how the ground is moving over time. We have XYZ tilt data, so that's measuring not the up and down, but how much the ground is physically tilting. Very, very important data set. We're measuring the data from thousands of earthquakes, another XYZ and magnitude data set, and every single earthquake also has parameters of how the ground has moved around it. We have frequency data of sound and acoustics and tremor going on underneath the volcano related to that seismic activity. We have gravity data. As you move stuff around in the subterranean world, you are changing the local microgravity as well, and we can detect that. We have imagery and videos from multiple webcams set up around the crater, all pointing towards where we know these lava fountains are going to be. We have high-resolution visible and thermal infrared videos of these eruptions, potentially in 8K resolution. We have satellite visible imagery, LiDAR, backscatter from multiple satellites with multiple various time and spatial resolution. We have air quality monitors scattered around the island of Hawaii, looking at changes in gas chemistry, how it's affecting local populations. We are incorporating weather forecasting into our models of where the ash is going to go, the fallout of ash and volcanic gas. We need to know if it's going to rain on that day, if there's going to be one of these volcanic gas plumes. We are collecting gas chemistry measurements from monitors set up around the crater, spectrometers measuring multiple elements at once, different elemental species, isotopes, ratios of those elements. We've got helicopters doing flyovers to assess changes in activity. We have written accounts and observational data from those scientists. Again, we're not forgetting that important qualitative data. We have the sampling of fresh lava from lava flows. Does this look like anybody else's Monday morning? Probably not. But this is the reality of what the scientists are having to do. We have the physical collection of material falling from the sky, and we are also then analyzing all of that data at every single time. Basically, there are buckets set up all around the volcano, and they go out after an eruption, take that bucket and put a new bucket in its place. We are then measuring the physical thickness of the ash fall all over the area. We need to know the amount of ash that's erupted during every single event. We are then rapidly processing all of that material we've collected, the size, the shape, the morphology, how dense the material is, the chemistry of the material of the products. We're not just analyzing the bulk material, we're looking at the glass, we're looking at the crystals, we're looking at the gases. And then we're also doing microscopic geochemical measurements on the tiniest points to assess how the magma is actually evolving every single episode. That is a lot of data. And all of that is being collected for every single one of those individual fountains that we saw, and also in between as well. They are huge data sets. So the challenge is not necessarily the collection of the data. It is in some cases. Not for these guys. This is one of the best monitored volcanoes in the world. It's great if you can do all the monitoring, but now you need to analyze and interpret all of that data to predict what is coming next. And therein lies the next challenge. So you can start, plotting multiple things at once. So for example, here, this was an eruption in 2018 over a period of about 5 months. We've got earthquake data on there. We've got the ground displacement data from GPS stations. And then we're also tying it to observational imagery so that we can tie the physical data to the observations. What did the volcano actually look like at this time? And so those are good. It's starting to get a bit of a busy plot, but we can just about deal with it. If we then start adding more and more of these data sets on top of each other, this is now looking at lightning data. There's also volcanic lightning. We don't really see this in the Hawaiian eruptions, but in bigger explosive eruptions, we do. So in these kinds of papers, they're looking at the number of lightning strokes per minute. They're looking at the currents that's detected. They're looking at the height of the eruption cloud. They're looking at infrasound and acoustic responders to the thunder. And they're able to lay out all of that time series to maybe also look for patterns as well. It's getting more complicated. But if you were to take all of that data that I showed you before, all of those different data sets, and try to plot them all on one single graph, it may come to something chaotic like I'm going to show to the next slide. If there's any astrophysicists in the room, they may have seen this figure before, or they may instantly recognize, well, that is just horrific. But there is a lot going on. There's about 15 different data sets, all attempting to be plotted on one single plot. And that's what we don't want to do. And so in the volcanic sense, this is actually as far as I think they're going to allow it to get. This is that 2018 eruption of Kilauea, and them trying to plot as almost everything they can on one single data point. So we have that earthquake data, we have the ground surface data, we have the chemistry data, we have lava flow data, lava lake data, we have geochemistry, we have the viscosity of the magma, how much the eruption rate of the volcano is. That's great if you can plot all that, but it's no good if you're trying to recognize a pattern of what's going on, which is where we need the analysis. And this is where things are going to go in the volcanic world, hopefully. So what I'm going to do now is play you a video from one of those recent episodes in 2025. This was episode 38 of Kilauea volcano just in December last year. And this is one of the webcams that is basically capturing one of the lava fountains. Now, all of the data I showed you in the last graph is all kind of physical point data that you can easily plot up. This is obviously downloaded at lower resolution, but I imagine this original footage is going to be in 4K resolution. There is a huge amount you could learn just from this one video alone. So the processing power that we need to be able to analyze not just the point data, but also the imagery data as well is absolutely incredible. What you'll probably notice as this video is going on is some of the ash is getting quite close to the camera. And this presents another one of those problems. We talked about, maintenance and putting instruments out and the need to automate these instruments. Thankfully, this is an automated webcam. It is live streaming, but there's only so much it can do when the fountains decide to change direction and start throwing material in a different direction. As you can see, this ash is now getting much closer, and this camera, without knowing it, is basically within the final seconds of its life. And so The data collected from this webcam means that at some point the scientists will have to go out and put another webcam somewhere else. So it comes to this question of infrastructure as well as maintenance. I think we should just take a few seconds of silence as this happens. Literally the final seconds recorded by the webcam on Kilauea there. And there we go. And they weren't able to retrieve it. Everything that's collected there is because of the live streaming and the telemetry being able to receive the data. So the telemetry is also incredibly important. So thank you, Webcam 3, episode 38. Quickly moving on to earthquake data for a little bit. We're focused mostly on volcanics, but we'll touch on just earthquakes on their own. There are over 20,000 seismometers around the world collecting earthquake data. And a lot of these came about, again, during this boom of instruments being put on the ground through the late 1900s, so the 80s and the 90s. And again, we can see that there's kind of this jump through the 90s, through the 2000s, of the number of small earthquakes being recorded. You can see that in that graph in the top left there. So the number of small earthquakes that we're detecting is much greater because we're putting more instruments out around the world. And this is mainly down to accessibility. We can now deploy them not just on land, but on the seafloor. We can deploy them in remote locations. We're lowering the cost of the technology. We've got a lot of actual Raspberry Pi technology that we're able to make homemade seismometers out of now. So accessibility and cost and deployment are really key for seismometers. And what this has allowed us to realize is there are over 1 million earthquakes that occur around the world every single year. Most of those are undetectable. In that graph you see on the bottom left, it says in 2025, there have been around 700,000 earthquakes. But we're probably underestimating the small end of the scale because they're so small, and you only pick up the earthquake if you're close enough to your seismometer to be able to detect it. So think of that data set alone. Just for 2025, almost a million data points, all of XYZ data and the magnitude as well. It's a lot of data to work through. Just again, not to scare you for your trips going out around the Bay of Naples in the next few days, just in Naples alone in the last year, there were 8,000 earthquakes in the last year. 7 of those over magnitude 4, but no bigger than 4.6, but over 8,000 of them very, very small, under magnitude kind of 2. So it's quite likely some earthquakes have even occurred today in Naples, but they were just too small to detect. So again, not to scare you or worry you for the next few days. Tsunami data is also reliant on huge numbers of buoys and floats all around our ocean. One of the examples of these data sets is shown here, over 1,000 different drifting buoys, 400 of them moored as well. Some of these are even tsunami meters. So buoys are normally collecting data such as the wave speed, the velocity, the water temperature, also maybe atmospheric data as well. So this is an incredibly important network. Everywhere you see a small kind of diamond or rhombi is one of these tsunameters. So these tsunameters are specifically placed in places around the world where they're hoping to detect places where tsunamis usually occur. A lot around the Southwest Pacific or Japan or the American seaboard or the Caribbean as well. So there's a lot of also oceanographic instrument data that is helpful for hazards because we need to know what the ocean is doing in a tsunami because we need the pre-model, and we also need to know what's happening during the tsunami itself. Another data set of floats that are in the ocean are one we call Argo floats. Argo floats, there have been millions of profiles collected from these, and currently there's over 4,000 Argo floats scattered all around the ocean, and you can see the locations in that map there. And each one of these floats is going down into the water column and collecting depth data as well. So we're looking at profiles of pressure, temperature, salinity, how salty the water is, sea currents, wave heights, swell, and even atmospheric data. And all of that data is again incorporated into tsunami models, forecasting what the state of the ocean is the second a tsunami begins, so they can forecast how long it's going to take to cross the ocean. That example you see in the bottom left there is a tsunami from the magnitude 8.8 earthquake in Kamchatka, Russia last year as well. But we need to know all of that ocean data to forecast how many hours it's going to take for that tsunami to cross the ocean. And then whilst it is crossing the ocean, we're also measuring all of those same things and getting that data in real time. maybe real time. You can see there for the Argo data network, it actually takes several hours for that data to arrive live. So again, we're missing an area. We need that real time to be able to get these back. So now we move on to a fairly different, these are underwater observatories. It sounds very Jules Verne. Underwater observatories, people in kind of like water suits, walking down on the seafloor very slowly, collecting data. Unfortunately, the reality is these underwater observatories are not human-manned. They are automated underwater observatories. The example I'm going to show you here is one off the coast of Oregon, about 400 miles west of the Oregon coast at Axial Seamount. You can see it there kind of in the center. This is an underwater volcano. It's one of the most active underwater volcanoes in the world. It's not particularly hazardous. It's quite deep. It only erupts lava that we know about so far, and it's not really going to cause an issue at the surface. It last erupted in 1998, 2011, and 2015. But because it's frequently active, we've decided to set up an underwater observatory to monitor what this underwater volcano is doing and, again, collect all of those kinds of data sets you see down at the bottom. So this is what the cabled array looks like. Essentially, there are several different monitoring stations scattered around the underwater crater, and all of them are fiber optically connected by cables back to the shoreline. So all of the data that's collected here is real time. It is autonomous, it is real time, time series data coming from multiple places around this volcano. So we're collecting some of the similar data that we saw before. We're collecting earthquake data, we're collecting ocean chemistry, ocean pressure. We're looking at, there's even video cams, there's live webcams down there as well from time to time. Hydrophones, pressure meters, tilt meters. There is such a huge variety of data being collected at this underwater observatory. Here's kind of another layout of what is also scattered around that caldera. All of those orange dots you see are an ocean bottom seismometer picking up earthquake data. All of the little sort of triangle transponders you see, those are all listening out for acoustics. And then there are floats collecting vertical profiles within the water as well. Again, remembering all of this is automated. This is probably the best example in the world, but it's not the only example. There are other underwater volcano observatories in our oceans. And like I said, there are also places where you can go to access live webcams of the hydrothermal vent fields in this region. Really incredible data collection coming just from these underwater volcanoes without the need for any boots on the ground. And again, they're also starting to put this data one on top of the other. So we've got the elevation data, so the physical ground movement of the inflation. We've got earthquake counts by month or by daily counts from different instruments. And they're starting to overlay, some of those different data sets and to look for patterns. Like I say, there are many more instruments. This is just one example from a recent paper. And again, that data is also tracking to very recent time. This was almost live, so this goes back to the very end of 2025. This is the inflation data going basically to the end of last year. And what they're looking to do is see, can they actually predict when this volcano will erupt again? They were hoping it was in 2025. It's not happened yet, but they're hoping for it in the next few months. Like I say, underwater volcano, a mile deep that won't cause anyone any problems. It's the only time we're wanting a volcano to erupt. Because now the instruments that are down there since it last erupted in 2015, the data we'll collect from this is incredible. So now we're going to kind of come to the end of this and talk a bit more holistically about, what are our aims? What do we want to do with all of this data? How do we even begin to process it? And I think there's a few different eras that we've fallen into within this realm. We first started off in the era of big deployments. This was our 80s, 90s, early 2000s of satellite, ground-based equipment, so our seismometers going out all around the world, and then starting to collect that data. Where I think we are right now, we're in this era of big data compilation. We're recognizing we have all of this data around the world, and we're now starting to bring it together. Big international collaborations like the Smithsonian program, bringing together all of that volcano observatory information and presenting it in a nice, publicly available database that anybody can access and start looking at that data. But where I think we are about to go to is now the era of big data analysis. We have the compilations, we have the archives, we need to just start getting to the big analysis and doing pattern recognition. All of those different data sets we're collecting, we need to know what the relationships and patterns are between each of them. With just one of the data sets, you can't do much. With two of them, you can do quite a bit. Imagine what we could do if we could actually process all 20 of those data sets at once. And so this goes back to that first theme. We want to be able to continuously analyze real-time, autonomously collected, multivariable time series data. We want to be able to recognize the patterns between those different data sets, different variable parameters, also incorporating in our own observations. We want to be able to run models from that analysis that can hopefully inform probability models, risk modeling, and helping us forecast what might come next. And so that kind of forecasting is what volcano observatories, geophysical observatories can do to inform authorities, stakeholders about what might be at risk within their communities or regions. So the choices that kind of lie ahead of us, I alluded to this more towards the beginning. What data do you actually choose? How do we prioritize where we collect the data? Which volcano do we choose to collect the data on? What data do we collect? And can we prioritize it? And can we even afford it? So are we just going to collect earthquake data? Are we just going to collect the chemistry data? So we have that choice to make as well. Who decides that? That's a really critical point as well, because everybody will have differing opinions. So again, is this decision being made by the observatory but completely by themselves, or is it coming from higher up? Is it a geopolitical decision? Is it a governmental decision as well? Do we monitor some systems robustly or all equally? If I give you 20 seismometers and you've got 20 volcanoes, do you put one seismometer on each? Or do you put all 20 on the one volcano you think is probably going to erupt the most? These are the questions that observatories have to play with. How do we know what we don't know? There are still impacts and risks happening that we haven't experienced yet. So our knowledge sometimes is limited because the event hasn't happened for us to recognize. But hopefully this is where pattern recognition can come into play for us. And similarly, are there patterns we are yet to recognize? I showed that graph before with about 20 different data sets all on at once. It's very hard for the human eye to look at that graph and instantly pick out relationships and changes that are matching with each other. But potentially we could use softwares like JMP to actually dig into this kind of data analysis. So this is kind of the final point. Do we actually have enough data already? Do we now just need to be analyzing all of the big data? Obviously, we shouldn't stop collecting the new data. We need to keep collecting that new data. But the archive of decades, if not hundreds of years, of volcanic and earthquake and tsunami data that we could go through and do this big data analysis is really something that we need to go on to. So finally, where do I see JMP playing a part? So this is where I throw it onto you for you to decide the best tool within JMP that could actually analyze all of this data. So first of all, we're trying to utilize these big data compilations and archives that we already have. We're trying to find this pattern recognition from well-monitored and well-studied systems, like I showed you with Kilauea. The amount of data we have for just that one volcano could potentially train how we forecast volcanic eruptions for the rest of volcanoes around the world. No volcano is the same, and things are going to be different, but you could learn a lot just by doing so much on one volcano. Training the automation of monitoring reports. All of that data, you somehow need to summarize it into one report telling you what's happened during that eruption or during that episode. It's very hard to do that if you have 20 data sets, but something like JMP might be able to actually summarize the key variables, the key components that you need to feature. Designing experiments, so this is where our DOE experts come in. How do we design our experiments to identify the triggers of different events? If we've trained a system to recognize patterns really well, can we design experiments that can identify when that pattern is starting to begin again? And potentially, can we use that in forecasting? Can we set up our monitoring networks with something like JMP Live? So all of that data is coming in, and it's already being continuously analyzed, not just being stored in large data archives as well. How do we better utilize our observational and human-oriented data by means of things like sentiment analysis and qualitative interpretation? This comes back to some of the stuff we talked about at the beginning, how important observations and imagery is alongside the physical scientific data. And the final point of how do we train the next generation of geoscientists? I can tell you, I did not come across JMP through the entirety of my undergraduate, graduate, and even postdoctoral research, education, and career. I did not come across this software. And I say it jokingly, but the amount of analysis I could have done with this software quickly would need to be training our next generation of geoscientists early on in their undergraduate education, how to not just think like geoscientists and learn the context, but to also think like a data scientist at the same time. So we've gone through kind of the 4 key points there. We looked at how geohazard data has evolved around the world, how the different types of data sets that we've dealt with. We've talked about some of the limitations that we have for data, the choices, the prioritizations we have, and I'm not going to read that again. I've said that sentence far too many times already, but essentially the goal of what we want to do with monitoring geohazard data. And then that final one that started it all off, is our understanding limited to our physical data just from scientific instruments? Well, no, we need to incorporate that qualitative human data as well. And this is just a really nice example from about a year ago, that 2018 eruption on Kilauea in Hawaii. They took Facebook posts and they did sentiment analysis on Facebook data throughout the entirety of this eruption. They saw how people were engaging with information put out by the Volcano Observatory. Was it a like, love? Hopefully not a ha-ha. But was it angry? Was it sad? Was it people liking data? Were they just liking or were they commenting? Were they sharing? That data was actually really critical to making sure they understood what people understood on the ground as well. So this kind of social interaction data alongside the eruption data creates this like picture of the entire eruption episode, not just of what the volcano is doing, but what the impacts and how it was being felt by the local communities. So incorporating in that human data and also historical data is so important. And that brings us back to our final points. Where we are today is so much data. There is so much that we can do, but we should always remember our origins of a science, the origins of our first data collected. And it's thanks to just 2 simple letters that we have those very, very first observations of volcanic data. But it's not a replacement. The physical data is not a replacement for these kinds of observations. Because of those 2 letters, we know more about this eruption than we probably would have done by just analyzing the rocks left over on the ground. And so if you actually want to read those letters, I've put those in that QR code there. They're quite a hard read. It's not just observation, it's human emotion as well. It's what Pliny was actually feeling when he was writing these letters about watching the eruption of Mount Vesuvius. So hopefully that's given you some insight into the vast amount of data we have in the world of geohazards. And I want to thank you all for your time and having me here this week. Thank you.
Thank you very much, Sam. I do appreciate the insights. And I imagine that there are a lot of people in the audience who frequently lament how data poor they are and now may be wishing, well, I don't want to be that rich.
Yeah.
Maybe. A quick question for you. How many people live in the shadow of these, and where is the greatest concentration of them? Of like who are in danger, who are at risk?
Of all volcanoes?
Yes. Or the largest one, or however you want to
largest areas around the world? I'd say probably the Tokyo metropolitan area. And not from an on-land volcano, but from an underwater volcano very close offshore.
Okay.
A potentially very explosive underwater volcano just into Tokyo Bay. Sorry for anybody who maybe knows Tokyo well, but again, it's why these underwater volcano observatory data is also very important. Some of the most dangerous volcanoes are lying just beneath the ocean surface.
Wow. All right.
Vesuvius in your backyard is very obvious.
Yes.
One that's just lying a few hundred meters beneath the water could potentially be incredibly hazardous.
All right, one more question. You've led me to. Where do you live, and how far away from a volcano do you live?
I guess it is very easy for me to talk about this one. I live in southwest England.
Okay, there you go. All right.
My nearest volcano, I think there's only a few kilometers in it between Vesuvius, or Iceland. It's almost equidistant between those.
Can you name that one in Iceland?
Eyjafjallajökull.
I knew you could. All right, there you go. All right, very good. We do have some time for questions from you all if you would like to ask one. We've got a couple of people with microphones out there. If you have a question for Sam, I'm certain that he will be happy to entertain it. Yes, right here in the middle. I guess Hannah, have you got, or Nicole, whichever one of you is closer. There we go. I picked the one right in the middle. Sorry.
Thank you.
If you would, tell us your name, where you work, and ask your question.
Nathan Barrow from Solve Chemistry. Hi Sam, great talk.
Hi Nathan.
You showed the data very early on about Mars and the moon, and I've heard of moonquakes and Marsquakes. What's the data situation like on those celestial bodies?
So moonquakes and Marsquakes, basically it comes down to how many instruments you physically have on the ground, which is not very many. So we know that they are occurring just from the very few small instruments, for example, on Mars rovers. They do occur. They are not occurring at the rate that we have them here on Earth, purely because there are no remaining plate tectonics on Mars and there are none on the moon as well. But it is still a physically moving body. The moon still is alive in some case. Mars still has part of its core semi-molten as well. It's still a dynamic planet, so you still have earthquake data, but more space exploration to that area would probably also put another seismometer on the next rover that, say, goes to Mars, or the next Artemis missions that maybe go to the moon will probably have a seismometer incorporated into that as well. So it's only going to build.
Other questions? Yes, Ole.
Thank you. Hi, Ole. I'm working for Rentschler Biopharma, which has absolutely nothing to do with volcanoes. But I wonder, how good are we in predicting volcanoes, in particular the intensity and duration, and if I can fly or not fly because Iceland has some issue?
Yeah, really, really good question. When it comes to the forecasting of volcanoes, we are very conscious to say in the Geohazards volcanologist world that we can't predict volcanic eruptions. What potentially we can provide are forecasting windows, and based on those things like patterns. As an example, the eruptions that are occurring in Hawaii at the moment are probably the best example of good forecasting windows. They've been able, based on the pattern, it's been 7 to 10 days between every single eruption episode. But that is just one very clear example. Volcanoes change the system every time they erupt. They don't completely flush themselves of magma when they erupt. If anything, most of the magma stays in the ground. So you don't reset back to 0.0 after an eruption. So even though you could look at an eruption pattern and say it erupted 60 years, then a gap of 80 years, a gap of 20 years, a gap of 100, you could take that average. But even after that, something could have happened dramatically inside the volcano, which will throw off that pattern completely. So it's a very difficult area to say that we can actually forecast things. What we look for are those warning signs. We look for the precursors and those lead up, and you just hope that you get days and weeks and not minutes and hours.
I think we have time for one more question. Yes, right here in the front, if you would.
Yeah.
Oh, geez. All right. If you're going to take the CEO privilege, just come on up here and do it. Ladies and gentlemen, this is our CEO, John Weiss.
That will teach me to raise my hand, huh? So, Dr. Mitchell, you mentioned lightning in volcanoes and electrically charged, I guess, particles flying around. So would you indulge me? I'm quite a coffee nerd.
Okay.
And there was a recent paper in the coffee industry talking about how to reduce static cling, and there's issues of how that affects coffee production or in coffee shops. And apparently it was inspired by volcanologists and some of your science.
Yeah, absolutely. So this is this incredible example of where different science fields can actually help each other out, right? But a lot of volcanology comes down to particle science. It comes down to grain size analysis and distributions, what the size and the shape of those grains are. And so for a lot of volcanic ash data, it's very electrically charged because the shape is not nice round spheres. Right. It's very, very small, it's cohesive. And so you can have electrostatic attraction between all those ash grains. And there's been a lot of work to try and understand how volcanic lightning happens in some eruptions and not others. Primarily, it's coming down to grain size, which is why in the coffee world, they're interested in how the grains are coheding. The finer your grains are, the more they're going to stick together. And that's going to influence like the quality and the production. So they've used the experiments and the analysis they've done on volcanic ash and lightning and how that's related back to grain size distributions of coffee.
Wow.
Your lab can smell amazing if you do it that way, because they also then use coffee as an analog material to test for the volcanic ash.
Cool.
That's excellent.
Right, well, thank you.
Sam, I want to thank you very much for your time. It was fantastic.